All right, so if we take a look at this right here, we want to graph this exponential function using transformations and then state the domain, range, and horizontal asymptote. So let's first start by just talking about the transformations that are happening. So let's start with the parent function. The parent function is the base, which is 4 here, right? The base of the exponent, which is 4 in this case, raised to just x. Oops, wrong color. That is always my parent function, the base to x. Now, how do you determine that 4 is the base of the exponent and 3 isn't? Well, look at what's being raised to 2x plus 7. The exponent is only on the 4, and if we were to follow PEMDAS, we would do the exponent before the multiplication, right? E comes before m in PEMDAS. So we do the exponent, then multiply by 3. So that is why our base is just 4. Our base is what's ever being raised to the exponent. So we've got 4 to the x. So everything else other than the 4 and the x, that's a transformation. So if we take this -3, okay, and -2, they are on the outside of the function. When transformations are on the outside of the function, and in this case, the function is the exponent, right? This is an exponential function, so the function is the exponent. When things are on the outside of the function, they're happening vertically. It's a vertical transformation. And when things are vertically transformed, it's happening to the y values, and we do as it says. So -3, multiplying by -3 is going to do two things. It's going to be a vertical stretch by 3. Oops, I forgot the word stretch. Vertical stretch by 3. And then also, this negative part, that's going to be a vertical reflection. A vertical reflection, right, is we're going from up to down, right? It's been vertically flipped. Well, that's going over the x-axis, so it's kind of hard to remember sometimes because it's vertical, but it's over the x-axis. It's happening to the y's, but what it looks like is it's going over the x-axis. So I remember it by thinking of it as a vertical reflection. If, something's going from up to down, it's going over the x-axis. That's going to be a vertical reflection. And then the -2, that's going to be a vertical shift down to, right? Because again, things on the outside of the function are happening vertically, and what they say are what they are. So it says we're subtracting 2. That means we're shifting everything, our y's, down 2. So that's a vertical shift down 2. Okay, now our horizontal transformations are in the exponent. So we look at 2x plus 7 to find our horizontal transformations. And there's two things happening here, right? We have 2 being multiplied times x, and then we're also adding 7. So order doesn't really matter when you're describing them, but if we were going to actually, on the next step when we actually algebraically find these out, we do reverse PEMDAS. So I'm going to talk about them in that way. So the first thing I'm going to look at is the plus 7. Now, everything in the exponent is opposite. That means opposite order of operations and opposite operation. So not only are we going to do the addition first, but it's actually going to be subtraction. Subtracting 7 would be a horizontal shift to the left 7. So that's a horizontal shift left 7. Okay, that's right there. The multiplying by 2 would really be dividing by 2, right, because we do opposite. So that's going to be a horizontal shrink, or sometimes it's called a compression. Can't fit the word in there, so I'm going to put it there. Horizontal compression by 2, or a horizontal shrink by 2. You could also say 1/2. I'd get what you were saying there, right? You can kind of think of like a accordion being smushed. That's what's happening to our function here. So that's actually 5 transformations, but it's only going to take 2 steps algebraically. Okay? Even though we don't necessarily need to know what each of these mean to successfully graph them, it's helpful to know them, because when I look at my graph If my graph, doesn't look reflected, it doesn't look stretched, I'll know that I did something algebraically incorrect. All right, so here's my function, and we need to actually find the points of what it would be. So when we're trying to find the points of our transform function, we always start with the points on our parent function. Now, the difference with exponentials compared to maybe some of the parent functions you saw in Algebra 2, right? X cubed, if that's your parent function, it's always x cubed. But because we've got b to the x as our general exponential function, for parent functions of exponentials, the base will always be different. So we can't just start with a set of points. We actually have to plug in numbers. So I'm going to plug in -1, 0, and 1. Okay, so when I plug in -1, 4 to the -1 is 1/4. 4 to the 1 is 4. And 4, no it's not. Well, it is, but we're doing 4 to the 0. 4 to the 0 is 1. 4 to the 1 is 4. Okay, so that is, that's my parent function points. If I wanted to graph 4 to the x, I would plot those points. But that's not what I'm trying to graph here. I'm trying to graph all these transformations. So let's take a look at what they are algebraically. So first thing, let's find our first horizontal transformation. So it's either the 2 or the 7, right? But remember, for horizontal transformations inside of the function, we do reverse PEMDAS. So we're going to take care of the 7 first, because we would do addition before before multiplication in this reverse PEMDAS world. But remember, not only do we do it in the opposite order, we do the opposite operation for horizontal. Everything's opposite for horizontal. So it says +7. That means we're going to subtract 7 from all of our x's. Okay? And when we do that, -1 minus 7 is -8. 0 minus 7 is -7. 1 minus 7 is -6. Okay? Now, to my y values, I've got a -2 and a times -3 on the outside of my function, right? The green things they're going vertical. But remember, with vertical, we do things in PEMDAS order. We just do what it says, right? It says multiply by -3. It says subtract 2. So we're going to do it in PEMDAS. We're going to first multiply everything by -3. Then we'll subtract -2. So let's go ahead and do that. Right? 1/4 times -3 is -3/4. 1 times -3 is -3. And 4 times -3 is -12. Okay? For the next set of transformations, well, now we're looking at the 2 for horizontal. Okay? It says multiply by 2, but it's happening inside the function. It's happening to the exponent. So we're going to do the opposite, right? Horizontal transformations, everything's opposite. So I'm going to divide all my x's by 2. Okay? And then if we look vertically, it says subtract 2. It's happening to the y, so I'm going to do as it says, and I'm going to subtract 2. So now I've got these points here. -8 divided by 2 is -4. -7 divided by 2 is -3.5. -6 divided by 2 is -3. If we're subtracting 2 from the y's, -0.75 minus 2 is -2.75. -3 minus 2 is -5. -12 minus 2 is -14. So these are the points of our transform function. These 3 points are the points that are going to allow us to accurately sketch a graph of this function with transformations. Now you may be like, why do we need transformations? I could just plug points directly into this. And while that is true, imagine if you were like, oh, 1. 1's a nice number to plug in. If you were to plug 1 into this, you would get -3 times 4 to the 10th minus 2. That number probably won't even fit in your calculator. It's such a big number. So in order to get the right shape, in order to get the points that are most helpful to graph, that's why we use transformations. Because if you just willy-nilly plug points in, you're not going to get the kind of graph you're looking for. Okay? You're not going to get points that are on a coordinate plane and tell you enough about the shape. So So let's go ahead. I'm going to rewrite those last 3 points, -4, 2.75. Was that a -2.75? Yes, it was. Then -3.5, -5, -3, -14. And I'm going to go ahead and put them on a coordinate plane. All right, so let's go and plot those. We've got -4, -2.75 will be right about here, and then -3.5, -5, and then -3, -14. Okay, maybe that's not, those aren't the best. We'll put that there. My stylus is not maybe not the easiest thing to use. Okay. We'll call these our points. All right, now it's a matter of understanding these functions enough to know how they're going to connect. So the first thing is, when we look at our function, we can pull our vertical asymptote right off of our function, because normally, 4 to the x is going to look like this. It has an asymptote at y equals 0. But we shifted our y's down 2. Everything moved down 2. So guess what? Our horizontal asymptote, it's going with it. So the horizontal asymptote of this guy is going to be y equals -2. Okay, on an exponential function, your horizontal asymptote is your vertical shift. So because we know that, we can get an idea of, okay, the graph's going to kind of flatten out along this part, right? It's going to follow the asymptote, okay? And then it's a matter of, okay, this is growth. The parent function was growth, but remember, we had a vertical reflection. We reflected it over the x-axis. So the reflection would have it looking something like this, right? It was obviously stretched and shifted a little bit, but that gives us the idea of, oh, okay, this makes sense to connect my points. This is valid. I didn't do something crazy. I mean, maybe I did, but like my graph makes sense. I can be comfortable, that my answer's true, right? It's kind of like if you were, in geometry solving for the side lengths of a triangle and you get a negative, you're like, whoa. Something's wrong. I can't have a negative side length. Same thing here. This matches, it's reflected, it's growth. It makes sense with our equation, so we can feel confident in our answer. Okay, last thing we have to state is domain and range. So remember, domain is always -infinity to infinity. It's pretty clear that it's going on forever this way, but even though this looks like it's pretty much straight up and down, it is technically, very, very slowly, if you were to zoom all the way out, growing in this direction. So our domain is -infinity to infinity. And then my range, it's always from the asymptote up or the asymptote down, right? It just depends on where the function is. So because the asymptote is at -2, but then it goes down forever, that's going to be, -2 to -infinity. But, if we have something on a number line, we've got -infinity here, -2 here. We're covering the zone, we read from left to right. So we would write it -infinity to -2. Remember, with asymptotes, we use parentheses because we're never actually going to hit that asymptote. We're just going to get really, really close. We're going to approach it. Okay, and yeah, you always use parentheses with infinity and -infinity. Okay, so that's an entire problem, an entire example.